Welcome to Quality Control in MRI Imaging. My name is Sarah Myers, and I will be your instructor for this part of the RAD 240 module. By the end of today's lecture, the students should be able to describe the different types of phantoms used in the magnetic resonance scanners, describe the importance of routine quality control testing of various MR parameters, describe the concept of signal-to-noise ratio, describe the concept of center frequency, and identify how to perform quality control testing for center frequency, transmit gain, geometric accuracy, and high and low contrast resolution. The goal of quality assurance procedures in MRI is to establish a standard of measurement for daily system performance and to document any variance in that performance. Any change in daily system performance can lead to larger problems. MRI is still considered a fairly new imaging modality and has seen tremendous growth and technological advancements in recent years. The ACR has developed an MRI accreditation program to keep MR image quality uniform across the country. New and used scanners will vary in image quality, and the program is designed to review qualifications of radiologists, MR scientists, medical physicists, and technologists, and also clinical imaging quality and the effectiveness of QC testing procedures of each site, applying for ACR accreditation. In an effort to increase level of image quality across the country, the ACR developed the Medicare Improvements for Patients and Providers Act of 2008, which mandates that any non-hospital institution performing advanced diagnostic services like MRI must be accredited by January 1st of 2010 in order to receive Medicare reimbursement. Phantoms are supplied by your vendor, and there should be one to use with each RF coil, including the body coil. Every site should also have an ACR phantom to perform the weekly and annual ACR test. The ACR phantom, along with test protocols, are designed to perform and examine several important instrument parameters with a single phantom. The ACR phantom is a short, hollow cylinder made from acrylic plastic and is filled with a nickel chloride and sodium chloride solution to simulate biologic tissue relaxation properties. Structures within the phantom are used to assess many different performance parameters that affect image quality. In general, QC phantoms will contain paramagnetic material in an oil or water solution. Common ions such as copper, aluminum, manganese, and nickel are often used. These materials are used to mimic biologic tissue and to shorten T1 relaxation time for strong MR signal. Relaxation times can vary with different material, the main magnetic field strength, and the temperature of the phantom. QC phantoms come in many different shapes and sizes and contain different geometric variables. The same vendor QC phantom can be used to test a signal-to-noise ratio and resonant frequency, while a different ACR phantom is needed to test for spatial resolution and linearity. There are several different tests that should be run daily and weekly using your daily phantom. That's usually supplied by the vendor, and the ACR phantom. The signal-to-noise ratio and center frequency tests should be done on a daily basis. Transmit gain, setup, table positioning accuracy, geometric accuracy, high and low contrast resolution, artifact analysis, film QC, and a visual checklist should all be done on a weekly basis, although artifact analysis and the visual checklist are things you should always be looking for every day during MRI. Setup and table position accuracy provides an overview of the condition of the MRI system's function. Table movement, console function, pre-scan, and table positioning and accuracy are tested. Ultimately, we want to make sure the scanner is operating safely during patient setup. Any problems noted with the scanner hardware or software, including scanner interface, computer boot up, table movement and table docking, if applicable, and table positioning should be documented. The ACR phantom should be placed in a head coil with the crosshairs engraved on the phantom centered and moved into the exact isocenter of the magnet. You will need to fine-tune the position of the phantom along all three axes using an MRI-compatible plastic bubble level. To verify positioning of the phantom, you can perform a sagittal and, if necessary, a coronal localizer. Once the phantom is correctly aligned, it stays in position for the rest of the ACR series of scans used for the weekly QC testing. Signal-to-noise ratio is simply the signal intensity of the image compared to the noise level in the image and expressed as a ratio. There are several factors that can decrease an MRI scanner's SNR, which includes a change of resonant frequency, a break in RF shielding, changes in scanning parameters, a fluctuation in the magnetic field strength, decreased RF coil performance, and change in the general system calibration. Signal-to-noise ratio should be calculated or run daily on the MRI system, and no significant changes should occur from the baseline SNR determined at initial scanner setup. The center frequency should be checked daily before any QC procedures are started and each time the phantom is changed. Center frequency is interchangeable with the Lamar frequency and resonant frequency. The center frequency is the radio frequency that matches the static magnetic field, or BO, according to the Lamar equation. The center frequency can be calculated using either the ACR phantom or the daily QC phantom from the vendor. Generally, the center frequency will be documented daily with the vendor QC phantom, and also again weekly with the ACR accredited phantom. To test the center frequency, set up the ACR phantom in the center of the magnet. Use the ACR T1 weighted axial sequence and run a pre-scan. Record the center frequency on the required form. You may need to repeat the pre-scan if your prescribed action's limit is exceeded. If the action limit is exceeded again, you must report a change to the service engineer and medical physicist. A change in the center frequency indicates a change in the strength of the magnetic field, which could be a result of cryogen pull-off, the presence of external ferromagnetic materials, shim coil failure, and/or changes in the current of the main coil windings. Cryogen levels on superconducting magnets should be monitored in case of any change to avoid a quench. Both liquid helium and liquid nitrogen levels should be monitored. Most vendors are able to monitor these levels remotely. If not, your facility should have a daily log sheet in place. Significant changes in center frequency of the magnet indicates changes in SNR. The center frequency should not change by more than 1.5 parts per million in between consecutive measurements. Transmit gain is a measure of RF power that is needed to produce a 90-degree flip of the patient's magnetic vector during scanning. While the scanner is pre-scanning, and after it establishes the center frequency, the MRI system then acquires several signals that contain different levels of transmit gain to determine the best RF flip angle for a given pulse sequence. Changes in transmit gain could mean that there are problems with RF transmitter or the RF coil anywhere along the RF path of circuitry. Changes in transmit gain measurements should be compared with the standard set at an acceptable testing, and if those levels are exceeded, they need to be reported to an MRI physicist or vendor engineer. Geometric accuracy, or spatial linearity, is the amount of geometric distortion in the image from displaced or improper scaling of the distance between points displayed on an image. The geometric accuracy is mostly affected by the homogeneity of the main magnetic field and the linearity of the magnetic field gradients. Low receiver bandwidth, poor eddy current compensation, and gradient miscalibration can also affect geometric accuracy. Geometric accuracy measurements must be within 2 millimeters of the actual true values of the ACR phantom. Most distortion is usually seen at the edges of the field of view, or gradually worse as you move away from the magnet isocenter. Edge distortions are expected, but we must take into account the accuracy of the MRI system when performing procedures such as surgical and treatment planning for biopsies, where distant measurements are extremely important. Geometric accuracy will also indicate an accuracy of the scanner distant measurement tool that can be used to verify the reported field of view. Field engineers usually perform geometric accuracy tests during the scanner's regularly scheduled preventative maintenance, or PMs. Reshimming the magnet or removing ferromagnetic objects such as paper clips, coins, or bobby pins from the magnetic bore can increase the MRI system's performance. High contrast resolution, or spatial resolution, is the MRI system High contrast resolution, or spatial resolution, is the MRI system's ability to resolve small objects. The ACR MR Phantom is used to test this and has inserts with arrays of holes in different sizes in diameters from 0.9 millimeters, 1 millimeters, and 1.1 millimeters. Testing parameters for high contrast resolution are those that can affect pixel size, slice thickness, matrix, and field of view. The ACR standard is a measurement of 1 millimeter or better in both directions. Usually, resolution is known as lines, pairs, millimeter, but here it is determined by the pixel size that a human eye can resolve on an image. The high contrast resolution is determined by the smallest array element, or the bar or rod, visible, that is completely separated by distance from the adjacent element. In other words, a small hole, array pairs, on an image above has a completely distinguishable hole from each other in both directions. The parameters selected to test high contrast resolution should be those that affect the pixel size, slice thickness, matrix, and field of view. Two-dimensional pixel size can be determined by dividing the acquisition matrix into the field of view. Low contrast resolution is the measure of the MRI system's ability to differentiate between adjacent tissues having minimal differences in signal intensities. There are several factors that can affect low contrast resolution, including increased noise, ghosting artifacts, improper phantom positioning, RF coil malfunction, and improper use of image filters. Usually, low contrast resolution is expressed in one of two ways. The first being the smallest diameter of an object with a specific contrast that can be detected, or second, the smallest difference in signal intensity that can be distinguished from an object of a specific diameter. The ACR phantoms contain 3 rows of low contrast objects that radiate from the center of the phantom in a circular pattern. Each row contains 10 holes of different diameters, from 7 millimeters to 1.5 millimeters. Slices acquired 4 locations within the phantom can provide contrast values. Action limits set by the ACR required scanners with a field strength less than 3T are to display 9 spokes of holes from a low contrast insert, and 3T systems should display 37 spokes. The ACR requires that the MRI system pass the low contrast resolution test on both T1 and T2 series. The MRI technologist should be evaluating daily phantom images for any signs of artifacts. Artifacts can differ according to image conditions, such as pulse sequences parameters, choice of RF coils, and with individual patients. Artifacts can be an early sign of equipment failure. The MRI technologist should become familiar with common artifacts and how they appear on images that are a result from the failure of one or more MR scanners subsystems, such as the radiofrequency system, gradient system, imaging and data processing, and magnetic field homogeneity. Each day, the MRI technologist should be checking each phantom image and looking for signs of ghosting, geometric distortion, changes in signal intensity, and any other interference with known parameters of the image. To ensure that their hard copy images that we print match the grayscale on our MR system monitors, we must, on a weekly basis, print a Society of Motion Picture and Television Engineer, or SMPTE pattern. From the SMPTE patterns, we can then measure and plot the optical densities of the grayscale by using a densitometer. The SMPTE pattern should be filmed on a 6:1 format. Verify that the 0 out of 5% and 95 out of gray level patches are visible and free from any artifacts. Artifacts should be noted if present. A film densitometer is then used to measure and plot the optical densities of the 0%, 10%, 40%, and 90% gray level patches. The optical densities are plotted on the QC chart, and any points that fall outside the control limits should be circled and noted. Part of running a daily QA phantom includes a daily visual checklist. Going through the motions with the phantom and positioning the coil and table and running the daily phantom QA will ensure that the scanner software and hardware are working properly before scanning any patients. These are QC tests performed by a medical physicist or system engineer. They are normally done on a routine scheduled basis, such as in 3 months preventative maintenance or a 3-month PM. Along with annual ACR testing, these tests should be performed on a regular basis or when there has been changes to the scanner or environment like hardware or software upgrades, a magnet quench, or facility construction. The ACR requires the following tests to be done on an annual basis to meet the ACR MRI accreditation standards. These are tests done by a medical physicist or a system engineer and assisted by an MRI technologist. The homogeneity of the MRI system magnetic field is an indication of the quality or uniformity of its field. Poor homogeneity can produce decreased image quality and artifacts. Changes in the homogeneity of the scanner can be due to ferromagnetic objects located inside the bore of the magnet and external ferromagnetic objects that may be close to the magnetic field. Magnetic inhomogeneities can sometimes be improved with gradient adjustment or shimming. The slice position test is done to make sure that the landmarking location is accurate and actually centered to the magnet bore. Mechanical problems with the table, positioning devices, or alignment beams can cause misalignment. Slice thickness accuracy is very important in an MRI. It is particularly important when performing certain procedures such as stereotactic and interventional procedures like breast biopsies. The thickness of each slice is determined by the transmit RF bandwidth and the amplitude of the slice select gradient. Errors in the slice thickness can cause interslice interference or crosstalk, which can change the accuracy of signal-to-noise ratio measurements in all pulse sequences. The ACR MRI guidelines call for 3 different measurements for volume coils and 1 measurement for surface coils. The annual QC test used for volume coils provides measurements of image uniformity, SNR, and percent signal ghosting in that coil. Tests used for surface coil measurements can provide only the maximum SNR of the coil being tested. These tests can indicate if the RF coil is functioning properly and if all the circuitry is intact. Other ACR tests performed annually by the medical physicist or system engineer are image intensity uniformity, which tests the RF coil sensitivity, percent signal ghosting, which measures the level of ghosting artifact on an image, and interslice RF interference, which tests how close together slices can be before causing interference with each other. Some optional ACR tests that can be frequently done are signal-to-noise ratio consistency and magnetic fringe field. These tests can be done annually. This concludes quality control in MRI.